Okay, so we're going to continue our study on measurement. Last time we covered the SI system or metric. This time we're going to go over US Customary Measurement System. And this PowerPoint will have some similarities to the last one. So those parts I might breeze over a little bit quicker, but I will focus on the new information as it relates to US Customary. So those who are keeping up with their notebook and the notes, today is November 2nd, and this will be a PowerPoint on US Customary Measurement System. So the US Customary System is a measurement used by the United States, and it is similar to the British Imperial System of measurement, but not identical. When we talk about the different units or the type of measurement we're using for length, we talk about using inches, feet, miles, for mass, slug, for force, we have pounds, time is second, and for temperature, it's Fahrenheit. For this activity, we're really just focusing in on measurement, and we're really just focusing on maybe inches and feet for the activity for today. So like we did in the last thing, let's do a size comparison of, let's say, the human hair as a cross-section, 2 sheets of paper, or the diameter of a paper clip. And in fractional format, I'm talking about 1/250 of an inch, 1/128, and 1/32, and then we have the decimal equivalents of 0.004, 0.008, and 0.031. And like before, we have our value or the number plus our unit, because without the unit itself, the value is of very little value to us. So, like we mentioned in the last PowerPoint, a measurement always includes the units, and a measurement always includes error because it's the best estimate of the quantity. Depending on the type of instrument you're using to record these measurements, it's still going to be an estimate. Scientists and engineers often use significant digits to indicate the uncertainty of that measurement. And now we want to talk about the accuracy and precision of our measurement, which would be a new concept. We did mention this in the last PowerPoint. So oftentimes these get interchanged. People use these interchanged. They say precision when they mean accuracy and vice versa, but they're not. So let's look at definition. Precision is repeatability, meaning the degree to which a repeated measurement shows the same result, as compared to accuracy, which is the degree of closeness of measurements of a quantity to the actual or accepted value. Okay, so let's look at some examples and kind of talk through that. Okay. On here I have my bullseye. I have high accuracy in the sense that I continually hit the kind of the center mark on my bullseye. Precision's low, however, because I'm not hitting it within the same point. Second example, low accuracy because I'm missing the bullseye, but I'm getting repeatability and precision because I'm hitting in the same point on my target. And then ideally, we have high accuracy, high precision. I'm hitting the bullseye, and I'm doing it in the exact same spot. Another way to think about this would be using, let's say, a scale for your weight. If I weigh, let's say, 170 pounds, that's the actual quantity, the actual accepted value for my weight, like it or not, 170, okay? When I get on the scale, it shows my weight at 165. And I get off the scale and I get back on, and it shows my weight at 165. I get off and get back on again, 165. Okay? In that circumstance, my accuracy is off because I actually weigh 170. Okay, so 165. Well, my precision is high because it's showing me the same, wrong, but the same number every single time. If I calibrate my scale before getting on, I get on, it shows 170 every time I get on, then it's highly accurate and highly precise. And that's what we're going for. Okay, so ideally, all measurement devices are both going to be accurate and precise. The accuracy is going to be dependent on the calibration. So like the scale, I have to make sure it's set to 0 before I use it. The precision is dependent on the characteristics and the capabilities of the measuring device. The precision of a ruler is not as good as, say, the precision of a caliper, which gets very, very small measurements. Okay, so this is dependent on the device itself. We record only to the precision to which you and your measuring device can measure. Right, so I can't use a ruler and measure out to, very large, really small increments or very, very long digits. It's just not going to happen. Okay, significant digits. We talked about this in the last PowerPoint, but we need to mention it again. It is the practice in science to indicate uncertainty in our measurement. And we talked about we would have the digits that we're certain about plus our estimate. Each of these is going to carry meaning, contributing to the uncertainty of the quantity. The digits you record for the measurement are considered significant. Include all certain digits plus one uncertain digit. However, when we get into fractions, which we do in US Customary and using a standard ruler, it becomes kind of fuzzy numbers when it comes to significant digits because I don't have digits. I'm in fractional form. So we'll talk about that in this PowerPoint. Again, as a general rule, if it's a digital instrument, read and record all the numbers, including zeros, after the decimal point exactly as displayed. For a decimal scale, or like the metric ruler that we used in the last activity, record all digits that you can certainly determine from the scale markings and estimate one more digit. So that's what we did in the last activity. For a fractional scaled instrument, which would be our standard ruler in inches, we're going to do some special consideration on how we want to deal with our significant digits. So a typical ruler has 12 inches that are graduated into smaller units, and typically these are going to be 16th of an inch increments. Sometimes it'll be a little bit smaller. Sometimes between, let's say, the 0 and 1, it'll go down to 1/32. So 1/16 is fairly standard. So if I look at then the distance between my 0 or starting point on my ruler and my 1 inch, I want to figure out what each of those little lines represents. I take the 1 inch and I divide that number in half, or find the midpoint. That's going to give me my half of an inch. I divide each of those in half again. I get quarters. Notice that each time I get smaller, the line gets a little bit smaller, and it'll be the same on the ruler. This lines will get a little bit smaller each time I do the division. So I have 1/4, 2/4, which is the same thing as a half, like in lowest terms, 3/4, 1 inch. So I can keep dividing this up into eighths now, and then 16ths. Okay, so each little line is going to represent 1/16 of an inch. And if I were to start at 0 and count across, when I get to the 1, I should have 16 16ths, which when I reduce to lowest terms gives me 1 inch. Okay, so let's do an example then using our fractional scale to record the length of this rectangle. If I take a closer look, I know that it is larger than 2 inches. I know that this is kind of my half of an inch point. So if I divide this in half, I know this is 1/4, this is 1/8. So I know it falls between 1/8 and the next line. If I count 1, 2, 3, this is 3/16. So 1/16, 2/16, which is the same as 1/8, 3/16. I know it falls in between 1/8 and 3/16. Okay. So how would I find the midpoint then between 2 and 1/8 and 2 and 3/16? For the fractions, I basically need to find a common denominator between the 8 and the 16ths that would give me that midpoint. So the midpoint between 2 and 1/8 and 3 and 16ths is going to be 5/32. How did I get to this number? Okay. I can think about dividing this in half and each one being a 32nd, or I could determine this using basically a common denominator of 32. Right? So I want to convert the 2 and 1/8 and the 3/16 to a denominator of 32. So if I take 1 and 1/8, I multiply by 4/4, which is the same as multiplying by 1, I'm not affecting the number. I get 4/32. I do the same thing for 3/16, so multiplying by 2/2 or 1. It's not affecting the number, it's just changing the denominator. I get 6/32. And then the average between the two, or the midpoint between the two, is easier to find. Right? So 5/32 falls directly in the middle of those two numbers. Okay, so our best estimate using our fractional scale instrument is 2 and 5/32 for the length of that rectangle. In order to start thinking about significant digits, I have to convert this to a fraction. So I multiply 32, I take 5 divided by 32, and I get a fraction of 2.15625. Now let's think back to the rule that we talked about. We said that if we're showing all these different digits, we're saying that they're all significant, and that we're certain about all of them, and the last one is a guess. So using the ruler, do we think it's precise enough to be certain about all of these digits except for the last one being the guess? Probably not. So as a rule of thumb, this is probably not the appropriate number of significant digits. And so what we are going to do is, in a decimal equivalent, we're going to go to the hundreds. and that's as far as we'll go. If it's in fraction form, the smallest increment or measurement we will use will be 1/32. So no matter where it falls between 1/16 and let's say 1/8, we're going to say that it's at the midpoint as our best estimate. And if it's an equivalent in a decimal form, then we're going to go to the hundreds, and that's as far as we'll go. We won't use all those digits. All right, so let's look at the activity for today because it's your turn to kind of work this out. We're going to do 3.1b, which is very similar to 3.1a. The difference being in this case, we're using the US Customary or the standard ruler for that. So for the first part then, I'm going to record the distances starting at 0 to where the first line is. I want to write this down in fractional format first and then show me what the decimal equivalent. Right? So the first one here looks like it's like 1/4 of an inch or 1/4 inches. And my decimal equivalent would be 0.25 inches. Scrolling down, this is the exact same image as the one that we did in 3.1a. The difference this time is now we're using our US Customary ruler to do the measurements. Okay. We have 2 spaces on here so that we can do the fractional and the decimal equivalents and make sure that you're recording both. You will need to add the text box in order to type in your answers. Don't forget that theta represents diameter, so we're looking for the distance across, and r is going to represent our radius. I did have a bunch of questions about the text box. How do I add that in? And when I do, what happens to the rest of the image? So if I go to the Insert tab, click on Text Box, Simple Text Box. When I do that, it overlaps the drawing and it's somewhere not necessarily where I want. So I want to make sure that it's in front of text as the wrap text setting. And that way I can actually move this down and place it where I want to put it. So it'll overlap the image, but it won't completely remove the image behind that. So if I want to place it right here, I can, and then I can modify the size of this text box. And this will allow you to actually type your answers into the document. This is the same diagram, number 10, as we did in the previous activity. If you want to use the exact same objects, you can. For this, make sure that you include whatever the name of the object is, what measurement you're actually recording, the units you're using, probably going to be inches, and then the actual measurement. Number 11 is asking you to do an isometric view of this object. So you're going to need the isometric graph paper to do that. Make sure that you're using the measurements given as you're doing the drawing. And finally, we have a conclusion question. There's just one. This can go right on the Word document. Please remember to use a color other than black as you are doing this activity so I can delineate your answers from what was originally there. When you are done, you'll submit this Word document along with this drawing from your notebook on the LMS, and then we will move on to unit conversions.